going to do some math, starting with arc length. And I can now erase my reminder to start recording because I am currently recording. Now, with arc length, you have a function in blue. That's a nice, pretty smooth curve. If you want to know its actual distance, its length, you can start by cutting up the x-axis into a bunch of little pieces. So let me get my pen going. So we've got our lower limit A, our upper limit B, and then cutting it up into a bunch of pieces. Now, you don't have to make these delta x's be the same size. But if you think about what's going on, it's easiest to think of them as being the same size. And you can probably imagine these delta x's becoming smaller and more of these points coming into play. And as more points come in, when you add up all these straight lengths, you're going to get a better and better approximation of the actual distance. So we're going to look at finding the distance between 2 points, any 2 consecutive points. And we're going to use a very, very famous theorem, a very well-known theorem to find this distance, this straight distance between 2 points. If you want, you can put in chat. Oh. If you stay after class, I can try to help you with the issue of the bad request and get that figured out. And I'll get to the go formative thing later. So, yay, Pythagorean theorem. So I've got a right triangle waiting for us. Now, in calculus, we often use the letter S for arc length or for distance. So I'm going to make the hypotenuse be represented by the letter S. Then the horizontal distance is delta x. The vertical distance is delta y. And Pythagorean theorem. Now, if x is what we chop up into a bunch of tiny little pieces, then that's who I'm going to multiply and divide by. But specifically, I'm going to use delta x squared. You can see that the expression is not being changed. I'm really just multiplying by 1. Now, I can split and distribute the square root over multiplication. And while I'm doing that, I'm going to distribute the division in the fraction. And then the square root of delta x squared gives us delta x. Then as we continue to look at the formula, you probably notice what this first part simplifies to. What does that simplify to? Come on, you can get a right answer in chat. Woo! Yeah! And then plus, and take a good look at what that is. And I'm going to write it as delta y over delta x quantity squared. And does delta y over delta x ring a bell? Yep. It is the derivative of y with respect to x. And the delta x will become dx as I prepare to write that I'm going to add them. So that's how I find one of these distances. How do I add them all together? Integral. And I have a nice typed up version of this formula coming up in case you need that. And I want to emphasize that if this is dx, then my lower limit and upper limit must be the x values where I begin and end. So I'm putting a and b, understanding that those are the x values that this exists between. And now I'm going to bring up my typed formula if you didn't get a chance. You know, different versions of the same thing. And we're going to do a couple of examples, mostly for the sake of there's a certain type of integration that will sometimes come into play, and it's more an issue of algebra skills. And I also want to mention to you before we get into the examples. Now, this is an added bonus. This is not something you're going to be tested on. But I want you to think about this. I could have dealt with a curve that maybe went like this. And I've got my x and my y axis. And I could have looked at finding the length from y equals c to y equals d. Now the difference would be that I'm cutting the y-axis up into a bunch of pieces, which means that right here, I wouldn't have divided and multiplied by my delta x squared. I would have done that to my delta y squared. And let's look at what that does to the formula. So in the formula, we end up getting dx dy squared plus 1 times the delta y, which we would then integrate from y equals c to y equals d. And when we go to find dx dy, we are dealing with something that is written as x equals some function in terms of the y variable. In that case, dx dy is just the derivative of that function. So we can go either direction with this, but mostly your problems are going to be focused on normal functions. All right, example 1. Now, I want you to try to be ahead of me on this, but I realize that we only have an hour, and yeah. In an hour and a half class, I would give you a little bit of time to try and get this done before I got started. But me talking right now is me giving you time to get ahead. But I've got to point out the fun word. I love these words. Semi-cubical parabola. Oh, math comes up with some of the best words. All right, now I want you to notice that this is asking you to find the arc length between 2 points that are on the top half of this semi-cubical parabola, and thus we are looking at the positive square root, not the negative square root. This section down here is the negative square root of x cubed. So this is the function that we are working with. And I want you to see if you can set up an integral and solve it and find out how long that is. So hopefully you're ahead of me a little bit. I need the derivative. Before I take the derivative, though, I'd rather rewrite this. And now the power rule is going to be nice. And then I'm going to square that derivative. Technically, when I square a square root, I am dealing with the absolute value. But right now we're just going to use the positive root. My integrand is then the square root of 1 plus the derivative squared. And because the integral is set up with respect to x, I have to use the x coordinates of my 2 points as the limits, the lower and upper limit of my integral. And now it's time to have some fun. Now, some of you have been doing u substitution in your head for a problem like this. It's actually good to reach that point. If you can do this in your head, or just write less, but still be very accurate, you can feel free to do so. If you might make a mistake by writing less, write more. It's more important to be accurate than to be quick. And hopefully everyone sees that we want our u to be the expression under the square root. And hopefully you are beginning to recognize that you can just multiply by 4/9. And then I'm going to change the x limits into u limits. First, I have the lovely plugging in 1 times 9/4 plus 1 gives me, oh yes, a fraction, what I always wanted. And then plugging the 4 in, I get 1 plus 9 is 10. Yay, nice. And then everybody practices integrating. Add 1 to the exponent. 1/2 plus 1 is 3/2. Multiply by the reciprocal. Okay, why did you... What? Okay, it closed. The entire thing just closed on me. I don't know why. All right, we're back. Hiccups. Internet hiccups. Yes, autosave. Autosave saves our lives. Oh my goodness. Now, the rest of it's pretty straightforward, so I'm just going to show you the final answer down here because that'll save us a little bit of time. And we have found the arc length. Yay! All right. Now, the next one is interesting. Are you ready for the next one? And I realize, correct, you don't need to simplify once those numbers are plugged in. So that means that you can leave your answer at that point, or once you have plugged those numbers in, whatever it looks like at that moment. Are you ready for more? Yeah. Okay. This next problem is a little bit different. First of all, it's asking you to find an arc length function based off of one particular point. So my initial point P naught at the point 1, 1 right here, I'm going to look at variable x going anywhere along here in the domain of the function. And what is the domain of this function? What is the domain of this function? Right? We have a natural log, so only positive numbers can go in. So we're looking at x going anywhere from larger than 0 to as large as we want to go, and getting a function, and the function is going to be named s for arc length with respect to x. That tells me the distance between P naught and whatever x coordinate point I land on. So what we're going to do is, first of all, I need to set this up as an integral from my initial point to my x coordinate. If I'm dealing with respect to x, then I'm actually working with the x coordinate of this point to some general x variable. However, it is bad math grammar to have the variable of the integral match with a variable on one of the limits. But the variable that we use for integration is just a dummy variable that is just a placeholder. So that means that I can change it to any letter I so desire. Typically, people use the letter T, but you can use any letter you choose. And now I want to look at this as a function with respect to t. As I create my integrand. Now, we're going to spend a little bit of time on the algebra that's going to go on here because it's crucial that you see this. It's a typical type of integral you might be asked to solve. So I have this one plus, and then I want to take the derivative and square it. The derivative with respect to t is 2t minus, and then I have 1/8, and the derivative of natural log t is 1 over t. And so now I have the expression for what is under the square root. Now carefully square your binomial. Square the first term minus 2 times the first times the last plus the square of the last. And take a good look at that middle term. What does it simplify to? Yep, it simplifies to 1/2. So I have right here minus 1/2. And then I'm able to add my like terms. And over here, I can only add the like terms of 1 plus negative 1/2. And do you see anything interesting? Do you see a fun little pattern emerging? When we squared this binomial, we got this, but with a negative 1/2, not a positive 1/2. And this is a unique type of integral that for some reason textbooks love to throw your way to play with the algebra. And if you don't see this algebra trick, you could end up getting very frustrated. So the entire piece under that square root factors into a perfect square with a plus instead of a minus with the 1/8t. And then when I remember that that's under a square root, I'm super happy. Yeah, it's beautiful. It's just so pretty. If only life could always give us problems this pretty. Now, when I square root a square, there's actually an absolute value there. Ooh, that rhymed. But we're going to look at writing it without the absolute value. My integrand is now in place, and I am now ready to integrate. All we have done so far has been algebra. And always pull constant multiples to the side and then recognize that you're integrating 1/t, and the integral of 1/t is natural log of t. Normally absolute value, but the domain we're working with is only positive numbers. Then we need to plug in the x minus plug in the 1. And what is the natural log of 1? 0. This is the function for arc length with respect to x. And I'm going to now show you the graphs of the original equation and the arc length equation and talk about what we just found here. That was what I call fun algebra, not way too much algebra. So figure 8 is the problem that we began with. We have our initial point, and this is showing x being to the right of 1, so we are integrating technically from 1 to x. And if I decide to put in a particular number, that will stop it at that particular number and find me that distance. And whatever that number is over here, the y value is that distance. Now, there's some really interesting things to notice here. First of all, look at figure 9 and notice that it goes through the x-axis at 1. Does that make sense? When x is equal to 1, it is asking what is the distance from x equals 1 to x equals 1, and that distance is 0. Then when I'm dealing with x being numbers that are greater than 1, like 2 or 3, I'm getting farther and farther from that point. My distance is growing, and I have a positive distance. But why am I getting negative numbers in between 0 and 1? Because we were supposed to be finding arc length. There are a few really interesting things to take note of. For one, if I am integrating from 1 to 1/2, I can negate and swap those to go in the proper order of smallest on the bottom, largest on the top. But you could also look at it as an issue stemming from the fact that we square rooted, when we square rooted a squared, we technically got the absolute value. And absolute value is really just plus or minus. So another way you could look at it is we chose a positive side of 0 by just using the positive square root. And then positive goes as positive as normally. If you are further to the right, you're getting positive numbers out. But if you are over here to the left, you're getting negative numbers out. It follows our natural system. If we wanted this to actually represent arc length, where this is really more displacement, we would need to absolute value. And I'm not sure I'm going to draw this, but I'm trying. Yeah. So it's actually, in a way, giving us more displacement than arc length. But I thought that was just really fun to take a look at. And the fact that you can create a function instead of just looking at one individual distance between 2 points, you can actually look at a function as a distance from 1 point. So that is arc length. Now, the next thing we're going to talk about is Euler's method. And Euler's method stems from slope fields. This is what would have been done in chapter 9, and I'm looking for, okay, it just tell me it didn't drop all the tabs I had. Oh, good. All right. So I'm going to copy this, and I want all of you to join this class. You're going to get to play with something that's really fun that'll help you understand what Euler's method is doing. So is everyone clicking on that link? And you're going to be working with this particular task. And so I've got to ask you, are you able to get to this screen? Okay, once you get to this screen, it's playtime. Delta x is the horizontal distance between any 2 points. And what I'm looking at is a solution curve in my slope field. Now, if my step size, if my horizontal distance is too big, I'm going to get an awkward looking solution curve. But if I make the delta x's small enough, I can actually pretty well predict what the solution curve looks like. And so sometimes you have a differential equation that you're not able to solve, but you can throw it into a data table and let the computer take over. You can also take this initial point, the one known point, and you can move it around and see how that changes things. You can also move your grid around. You can change the function you are working with. Come on. Okay. Oh, I think I have to bring that up and then go in, and then it lets me. Like, I'm just going to go, wait, it didn't, no. Okay, not working for me because it's trying to do something else. Anyway, I know that I did it earlier. Maybe it's because I'm using a test thing that it's not letting me change it. But play with that because this is Euler's method. This is what Euler's method does. Now, here's the thing. The only time you would ever not use a calculator or computing device with Euler's method is when you're taking a calculus test. Yes! If you had access to a calculator, you would not need Euler's method. But the use of Euler's method is very valuable as an application. What you're learning in this math class is how and why Euler's method works and what it's doing. And in order for you to show that you know what it's doing, you have to mostly answer problems without a calculator. Now, you can continue playing with that a little bit, and I'm going to come back over here to the notes, and now I want to show you what this is expressing. This was the best picture I found online. Maybe if I had searched longer, I could have found better, but whatever. What this is trying to say is the exact solution to the initial value problem is supposed to be this curve down here below. So it's saying that at the point x sub 1, the y-coordinate on the actual curve is the y-coordinate with x1 plugged in. So these are actual points on the curve. Euler's method starts you at one point that you know. You have one initial value. If you are in the middle of a slope field, you know the slope at that point. If you follow that slope for a certain horizontal distance, which in this picture and your textbook, they use h. I prefer to use delta x because it's more descriptive, but h is kinder on the algebra. If you go for that horizontal distance following that slope, it will land you at a y sub 1 value. Now that y sub 1 value is already having an error from the actual y value. If you had taken a shorter step size, you would have a more accurate answer. But once you have gone through one step size, then you just take a look at where you are located in your slope field and allow the slope field to tell you your new direction. You follow that slope for another step size horizontal of delta x, and that lands you at another y coordinate. However, it does have an error. But do you see that the error you are getting from changing direction is far better than if you had stayed on that tangent line? The error at this point would be way, way, way worse. Euler's method keeps you hugging the curve better as long as your step size is small enough and as long as you don't have any discontinuities going on. And then you can look at the point you have landed on in your slope field, figure out what direction am I now going, and then change course and follow that for another delta x. So that's what all the data in the table is giving you. If you look back at this, that was x. Let me just refresh it. There we go. So it's giving you x, y, the slope at that xy point, and oh, there's more. Okay, come on. Oh, no. It looks like it's supposed to go for more, but maybe it doesn't. So you can see, anyway, the table of values over there. Now, Euler's method is a formula. And I'm going to show you where this comes from. It's a recursive formula. And all it is it's coming from something you already know, the equation of a line. I'm going to show that again, but first I'm going to say you will be given an initial value. And that is the x naught, y naught. You are going to somehow have information about the slope, dy dx. And I'm just putting an m for slope because it's a quick communication with you. But that slope changes every time you go through the process. That's the most important piece of this process, is the fact that the slope changes from one iteration to the next iteration. And that's usually where the mistakes go. And so what I'm going to say is, I know who x1 is. So I'm going to write an equation of a line, and I'm going to say generic line y minus known y naught equals slope, which I'm going to put an m right now for, times change in x. You should recognize this formula for equation of a line, point slope form, something you're already familiar with. I'm going to use this as a tangent line, and with it, we have 10 minutes left. With it, I'm going to plug in x sub 1 into its x to find y sub 1, the y value. To do that, all I have to do is add the y naught over to the other side. So my first iteration's y value is equal to my initial y plus the slope times, and What is x1 minus x sub 0? The step size, the delta x. With an Euler's method problem, you are given a particular step size. You don't get to just use this any way you want because you're going to be testing on it. So they're going to tell you exactly what the step size is or enough information to find it. So if you look at it, what it's saying is to find your next y, you're going to take the previous y and add to it the slope at that point times the step size delta x. And I'm going to go through some examples with you, but I want to show you that that's what this formula is. It is saying to get each next y value, you take the previous y value, you add the slope at that same previous point, and then multiply by the step size. We're going to do an example together. And for the sake of time and pain, I changed this problem to only estimate for y at 0.2. And I want you to be aware that I have seen Euler's method show up in no calculator sections similar to this right here. You don't have a calculator. So everyone put on that multiplication thinking cap. Or perhaps it's too tight and it won't go on anymore. I don't know. But let's do this example together. And I'll talk you through how I like to set it up. And then you can choose how you like to set it up. I like to set mine up where I write down my initial value. And then because I'm given a particular step size, I know what all my next x's are that are coming. If there were more, I'd write more. I am given that this is my initial point. So I'm going to put that down. Then I like to prep my formula to find, oh, and I just realized I didn't finish. I'm told that the step size is 0.1. That means I know x1 is 0.1, x2 is 0.2, and if I had to go to 0.5, I would have to go 5 iterations, which is tiresome. And now I like to get my formula set up. The formula is drop down the previous y, add to it, and I like to reverse my multiplication order by writing the step size times the slope, because sometimes the slope ends up being a little bit of a longer formula. And what I can do is I can prep the others. I'm going to bring down whatever I get from the answer here. And then I'm going to add to it my delta x times my slope. So here we go. You may be given a table of values. You may be given a differential equation. But somehow any problem you're given has enough information to get through it. So the first thing I do is when I'm wanting to put in my slope to find y sub 1, I must use my sub 0 x and y coordinates. So I plug in x equals 0 and I plug in y equals 1. And I'm going to write more than I need to make sure that you see that it's coming from here. Y plus x times y. And also the drop down of the previous y. So again, I dropped the previous y, added step size times slope. And now let's do this without a calculator. 1 plus 0.1 times 1. Yes! Woo! For my next iteration, I'm going to take my previous y result, drop it down, add the step size times the slope, but very, 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 very important. I'm changing my highlight color. I must use my sub 1 x and y value in my slope formula to get this slope. I think one of the most common mistakes is to just keep using the same x that you used before, or simply to just plug in the... People do a variety of incorrect things. It is usually right here where the mistakes happen. Take your time to think about what you're putting in. And what are you... I'm distracted temporarily by Armand, I think is... Yeah. You were holding something up and it distracted me. I'm easily distracted, and I'm guessing so are teenagers. So staying focused on the math and not distracting each other. Let me go back over to here. And now I'm plugging in to the x's and y's of the derivative formula, the sub 1 values. 1.1 plus 0.1 times 1.1. Now, I'm going to say this. If I were on free response and this is where I was, I would call it a day. Or you can go ahead and risk your multiplication abilities. We're going to go ahead and do it because it's not a test right now. But my advice is when you are taking the AP test, you're good enough there, don't simplify and give yourself the possibility of an error. So we've got 0.1 times 1.1 says, move the decimal left 1 unit. No, digit. Ha, digit. Proper vocabulary. Then 1.1 plus 0.11, then multiplied by 0.1. Isn't this fun? Means I move the decimal point over and then add it to 1.1 to finally get 1.221. How much fun was that? Oh, okay. Now, class is over at 12:35, am I correct? Yeah, which is less than 1 minute away. So I made it, got through it. Now, very important. Make sure you understand where you are going to find your homework. You are going to go over... You are going to... Oh my goodness. Loading. I am going to post your homework number 1 in your AP classroom. Oh, the final answer was the 1.221. And what that was giving you was approximately what the y value was at 0.2 for the solution of this differential equation with this initial condition. So There is homework. Make sure you find it, and I'll put enough stuff up on Google Classroom to help you find it. But our time is up, and you need to go to fourth